Now let's talk about systems, variables, and processes. So, what is a system? A system is a part of the observable universe that we are analyzing, and the surroundings is everything else. To distinguish these, we use a boundary. And when we're solving problems, we select the system based on what question we're trying to answer, right? And as you can imagine, we're going to encounter many different types of systems. So we have to have a way to classify these systems. And one way in which we do that is we look at the types of mass and energy exchange that occur across the system boundary. So the example we have on the left here is where mass can cross the boundary and energy can also cross the boundary. So this would be an open system. And what we'll actually see is that when mass can enter or leave a system, that mass has energy associated with it. So in that case, you're going to have an open system. You can probably think of many different examples of that. The next one is where mass cannot cross the boundary, but energy can be exchanged between the system and the surroundings. And this is a closed system. So you might think of a vessel with some contents in it, but the vessel's a sealed container, so mass cannot enter or leave, but you could heat up the contents or cool them down, so energy exchange is permitted. That'd be a closed system. Lastly, you might have an isolated system. You see this in physics, right? If you're looking at the motion of a particle in a field, that would be an isolated system if you're looking at the particle because you're not analyzing mass and energy exchange between the system, which would be the particle, and its surroundings. So that's a good example of an isolated system. Of course, this isn't the only way that we classify systems. We can also do this based on the number of phases that a system has. And when I talk about phases here, I'm not talking about solids, liquids, and gases, but I'm actually just talking about a part of a system with its own properties and a uniform composition. So here on the left, we would have a heterogeneous system. And we call it heterogeneous because there's more than one phase, right? You have this green phase on the top. So maybe this is oil and water, which are immiscible. And both could be in the liquid phase there, right? So you would call that a heterogeneous system. And then on the right, we see just the single purple phase. This would be homogeneous. And again, I draw this distinction because we'll see cases in which we have a set of equations that may only apply to, say, homogeneous systems. So that's something that we need to be aware of course. Moving on, we can look at how we characterize the system boundary. Okay, so this is going to be another key feature in the problem solving process is what type of boundary do we have? How is that going to influence what equations we use or what assumptions we can make when we're trying to solve a problem? So let's look at the case in which we have heat transfer. And when a heat transfer is permitted across the boundary, we say it's diathermal. If not, we say it's adiabatic, which you've probably heard before. And you can think of that, right? So if you had a system that's very well insulated for the boundary, like on the outside, then that would be adiabatic. For mass exchange, we have an impermeable boundary when a mass cannot be transferred between the system and the surroundings. And then we have the case where the boundary is permeable. So mass can be exchanged between the system and the surroundings in that case. So, for example, if you have a permeable boundary, as I talked about before, you're going to have an open system in that case. Now, let's look at this on the bottom left. We have a stainless steel vessel. And here I wanted to introduce this term that you might see in problem statements where they say you have something that's rigid, right? And if that's your system boundary, that means your boundary can't move during the process that you're analyzing. And what we'll see is that means your volume is not going to change. And we have a special name for that type of process. So that's something that's important to look out for as you're trying to solve problems. After that, here we can look at the opposite case. Maybe the balloon is our system, and we see it's shrinking. So we would say that boundary is flexible because it can move throughout that process. And so the volume of our system can actually change. Now let's talk about variables. We're going to use variables to describe systems. And thermodynamic variables are known as state variables because they specify the state of a system, which I think makes sense. So state variables would be like temperature or pressure. These are common ones. And that's because they tell you what the conditions are in your system. And these state variables can be intensive or extensive. So an intensive variable would be one that's independent of the size of the system. Temperature and pressure would be great examples of intensive variables. And in contrast, extensive variables do depend on the size of the system. I should also mention that intensive variables don't depend on the amount of matter or the amount of particles present in your system either. So let's illustrate this distinction with a short example. So let's say I have one very large system, one very large lead block, and then let's look at the case in which I have one very small lead block. So we'll have this be block 1 here on the left, block 2 on the right. We could use different variables to describe these systems, right? We could use the mass. So the mass of block 1 is larger than the mass of block 2. We could use volume. The volume of block 1 is greater than the volume of block 2. We could also use the density. However, since this is a homogeneous system here with the lead block 1 and block 2 are going to have the same density, right? It's just a solid phase there, and they're both lead. So their densities are going to be the same. The density is independent of the size of the system and thus an intensive variable. Now, mass and volume are inherently extensive. Mass is measuring the amount of matter present in the system, and then the volume is a measurement of the space that the system occupies. So that depends on the size of the system, thus it's inherently extensive. And if we look at the formula for density, which is mass divided by volume, we see that we have a ratio of two extensive variables, and that gives us an intensive variable. So this holds true for other formulas as well. So if you look at another equation, like the one for molar volume, you have the volume of the system divided by the number of moles. You see that you have another ratio of two extensive variables, and this gives you the molar volume, which is an intensive variable. So that's an important relationship to have in your head. And also, I should make note here that intensive variables have more practical utility for our purposes in this course, right? Because they're independent of the size of the system. So when you think of tabulated physical property data, the intensive variables are going to be used there because you're going to use that data to solve problems for many different types of systems that you encounter. So that's why intensive variables are very important. Temperature and pressure are very common, and that's just because they're very easy to measure. So I just wanted you to be aware of those as I teach you about this and draw this distinction between intensive and extensive variables. So now that we have covered that part of this section, we can talk about how we classify different processes. And a common method we use is just by looking at what variables remain constant, right? So if we have a process in which pressure is constant, there's no change in pressure, we would call that an isobaric process. For temperature, this would be isothermal. And for volume, this would be isochoric. So that implies you might have a system with a rigid boundary that can't move. So the volume of your system does not change throughout the process, and thus your process is isochoric. Now, there's a couple other state variables in here that we'll talk about later. That's enthalpy and entropy. So delta H, that's the change in enthalpy. If that's equal to 0, you have an isenthalpic process. And if your change in entropy, delta S is equal to 0, this is an isentropic process. And finally, if there is no heat exchanged between the system and the surroundings, your process is adiabatic. As you can see here, when we talk about these different types of processes, that discussion we had about characterizing different system boundaries is very important when you're trying to determine what type of process you have. And you see that where you have like an adiabatic process, maybe your boundary is really well insulated, or you have an isochoric process, maybe your system there is rigid, so the boundary of your system is not going to move as that process takes place. So those things are all very important to understand. And the last thing I wanted to mention here is that we can describe processes based on how they are carried out. So we'll talk about reversible processes and irreversible processes later on. I'll make a special note here that an isentropic process is a reversible process. Okay, and we'll see that distinction become very important when we talk about entropy later on.